This is constitutes section 2.2, which hopefully we'll get to by the end of today, but we'll see. We'll definitely get to it next time. Let's start with a quick prayer. O Father, Son, and Holy Spirit, amen. Him our full grace and Lord's with thee. Bless thy family and womb. Bless for the name of Jesus. Lord, Lord God, pray for us sinners now, the hour of death and life. St. Thomas More. Pray for us. Heaven rise. Pray for us. Jesus, Real quickly, let me know if you're here. Michaela? Here. Quinn? Julia? Here. Daniel? Here. No other Daniel? Here. Olivia? Olivia's not here. Samantha? Here. Julian? Here. Claire? Here. Allison? Here. Lauren? Here. Bramble? Here. Samantha? Here. Brienne? Here. Nicole? Here. Cassandra? Annika? Here. Christina? Here. Decus?
Here.
Alexandria?
Here.
Annabelle?
Here.
Mayan?
Here.
Ariana?
Here.
And Leah?
Here.
Thank you. I didn't assign much over the weekend because I want to pick up our discussion near the end of section 1.1 by doing some additions, maybe some minor revisions as well. So I want to go right to the page that we ended off last time, which had to do with this plot. Gary makes reference to a term this is on page 63. It's not finding my projector, so it was very good. There we go. So this paragraph here is talking about the bubble that forms at the bottom of the plot where the temperature is the highest, rises to the surface. The vapor pressure inside the bubble acts to inflate the bubble, while the weight of the water near the above the bubble creates an opposing pressure that acts to collapse it. That's true. But the term vapor pressure is a specific term. It's an intensive property of different forms of matter that relates to what we refer to as volatility. A volatile liquid is a liquid that changes to a vapor quite readily. What it tells us is if a liquid has molecules that enter the vapor phase real easily, it means the molecules don't stick to themselves that well. And we'll talk about all those intermolecular forces when we get into chapter 6. But for now, I just want you to understand what the term vapor pressure is. Let's imagine a vessel where we have a liquid, and originally it's an open container, but then we put a top on it, and we put a pressure gauge in the top of that on the lid, okay? Now that pressure gauge is going to measure, when the liquid starts changing to a gas, it's going to measure the force per unit area that those gas molecules exert on the inner surface of that container lid, because that's what pressure is, force per unit area. Initially, there are no gas molecules in the space above the liquid, but over time, in the closed container, the concentration of those gas molecules is going to increase. And as they increase, so is going to be the pressure above that liquid. At some point, at a given temperature, and the temperature is remaining constant, we're going to reach a point where the rate that those molecules enter the vapor phase, evaporation, is matched by the rate that they recondense on the surface of the liquid. When we have that, balanced opposing rates, it's called a phase equilibrium. You don't really need to worry about the term equilibrium now. It's just a balance between two things. So If the rate of evaporation equals the rate of condensation, then at that point, the pressure will stop going up and remain constant. As long as the temperature is constant in that closed vessel, that pressure will remain there. That's what vapor pressure is. It's the pressure of a vapor in equilibrium with its liquid at a constant temperature, okay? Obviously, if I change the temperature, if I raise the temperature, the number of molecules entering the vapor phase is going to increase. And then the number of molecules, the pressure of the vapor in equilibrium with its liquid is going to increase. So vapor pressure increases with temperature. But at a specific temperature, let's say room temperature, different liquids will have different vapor pressures. Some liquids change to gas really readily. If any of you ever smelled nail polish remover, the main chemical in most nail polish removers is acetone. It's a very volatile liquid. So as soon as you take the top off that jar, you can smell the acetone right away. And you guys ever smelled nail polish remover? Okay. Acetone is a volatile liquid. Its molecules don't stick together that way, which means given the opportunity, the liquid happily vaporizes at a relatively low temperature. Vapor pressure is also associated with something called a vapor pressure curve, which is unique to the liquid for which we're measuring it. Now, you don't need to put this in your book, okay? You don't even need a definition of vapor pressure. But let's put here pressure. And the reason I'm doing this is hopefully it'll make sense out of a couple of the other things Gary has said. And let's say that we're going to arbitrarily decide that that atmospheric pressure will be here, right? So let's say that's atmospheric pressure. Now Gary tells us, when he goes back to the bubbles in the boiling water, we call this 1 atmosphere pressure. Okay? He says here, the vapor pressure inside the bubble acts to inflate the bubble, while the weight of the water and air above the bubble. The weight of the air above the bubble, that's atmospheric pressure. So as we said last class, I think we said, atmospheric pressure is the weight of the air above your head, wherever you are, relative to ground level. So if you're at sea level, the weight of the air above your head is pressing down on you. That's what we refer to as 1 atmosphere pressure. And I think in kilopascals, it might be 101 kilopascals, okay? That's the thing that's deflating that bubble. The bubble is only going to make it to the surface without collapsing if the vapor pressure inside the bubble at least matches atmospheric pressure. Otherwise, it's going to collapse before it gets to the surface. So let's say, and let's put temperature down here. Now, I'm not going to put units like 0 here, but let's say we were looking at it, and this is just a sketch, the vapor pressure of, say, acetone, that vapor pressure curve, okay? At a given temperature, and let's say down here, let's say this is room temperature. So let's say 25 degrees Celsius. And this scale could start anywhere, but because at every temperature, each liquid has a vapor pressure. So let's say acetone might be right here. At room temperature, it's a pretty volatile liquid, so its vapor pressure might be about here, but as we heat it, the vapor pressure curve does that, okay? It begins to increase exponentially. So if we look at this again as our original container, at room temperature, the vapor pressure would be based on this equilibrium, but as we increase the temperature, the number of molecules is going to go up. And it's going to go up pretty rapidly. Where that vapor pressure curve crosses atmospheric pressure, that means the pressure inside those bubbles match the weight of the air above the bubble. In other words, you don't collapse. So there is a definition of boiling point. The point at which, the temperature at which the vapor pressure of the liquid being heated equals atmospheric pressure, okay? And for acetone, I believe it's like 54, 55 degrees Celsius. If it's that low, say compared to water, it must mean it must be more volatile than water. There's another liquid, looks like acetone, looks like water, but it's not. It's called methanol, methyl alcohol, the lightest alcohol. It has a vapor pressure curve that's not quite as high as acetone. So methanols might be something like this. So at any given temperature, it's got a lower vapor pressure, and its vapor pressure curve doesn't cross atmospheric pressure till about maybe 65 degrees Celsius. Water is much less volatile than both of them. Water sticks to itself really well. So water might have a vapor pressure curve that looks like that, okay? And we all know that water at sea level boils at 100 degrees Celsius. So that would be the temperature where water's vapor pressure curve reaches atmospheric pressure, okay? Now, of course, if you're not at sea level, let's say you're above sea level. Well, the higher you go up, the less air above your head there is. So the less air pressure there is. And if the pressure's lower, so is the boiling point. So let's say you go to the top of a mountain, and maybe the atmospheric pressure isn't there, it's maybe here. Well, now the boiling temperature is not going to be at 100, it's going to be lower. And let's say you want to boil eggs, you want to make hard-boiled eggs, you top of a mountain, depending on the mountain, you might have to leave it in the water longer to cook it, because the water is going to boil below 100, and it's not going to get hotter than 100, which we're going to talk about soon. Any of you have pressure cookers at home or know what a pressure cooker looks like? Any of you? So the lid isn't just a pot lid, it screws on, doesn't it? Yeah, so it's a really heavy, thick pot. It's meant to withstand increased pressure, and the lid screws on. You don't lift it off, you screw it off. And there's usually a pressure release valve in the top. What's the point behind a pressure cooker? Well, if the pressure is higher than 1 atmosphere, then that vapor pressure curve isn't going to reach atmospheric pressure till it's above 100, which means things will cook faster in the pressure cooker. So if you artificially elevate the environment pressure in which this thing is cooking, what it's cooking in can get hotter if it's an aqueous solution, and most things are made mostly in water. Lowering the pressure lowers the boiling point, increasing the pressure increases the boiling point based on the definition of what boiling is, okay? Now Gary makes reference to that again down here. The entire pot of water is not yet boiling because now you're boiling. Only at this point when the bubbles rise to the surface of the water without collapsing. Why don't they collapse? Because the pressure inside the bubble equals atmospheric pressure. Is the entire pot of water boiling? Just before breaking through the water's surface, the bubble is only opposed by the atmospheric pressure above the liquid. One definition of boiling point is the temperature at which the substance's vapor pressure equals the surrounding air pressure. That's the best definition of boiling point. And it shows that the boiling point is variable because it depends not only on how well the molecules can enter the vapor phase, but it also depends on the pressure. The air pressure above the sample could be lowered by placing the sample in a vacuum chamber or by taking it to a higher elevation. This would lower the substance's boiling point because the bubbles would have less opposing pressure. And you can see that on my rough vapor pressure curve, which, by the way, I'm not going to expect you to reproduce on a test. Now, this is where I take some issue with what he says. Boiling point is also defined as a substance's highest possible temperature in the liquid state at any given atmospheric pressure. That's true. It therefore represents the highest kinetic energy the substance's particles can possess in the liquid state. I agree with that as well. As the temperature of water approaches 100 degrees Celsius, more and more of the molecules have their maximum kinetic energy in the liquid state. Now remember what temperature is a measure of. Is it a measure of kinetic energy, or is it a measure of, what word do we put in front of kinetic energy? Temperature is a measure of the what kinetic energy? Starts with an A. Average. Now why did we have to use average? Gary explained it to us a few pages ago. Because of the collisions of the particles. So this end of the sentence I don't agree with. Until at 100 degrees, all of the molecules are moving at the same speed. That's impossible. If that were the case, if all the molecules were moving at the same kinetic energy, number one, the temperature we're measuring wouldn't be average. And number two, the pot of water would disappear instantly. It doesn't disappear instantly. I can change the shape of a kinetic energy distribution curve by adding temperature, by adding heat. But I can't ever make all the molecules go at the same speed. And again, if we hearken back to this diagram, that I have on the board before. In other words, what would I change here? Maximum average kinetic. Because boiling water doesn't change what temperature is. Okay? So if we have number of particles or number of molecules, whatever, doing the colliding, and let's say we have kinetic energy here, at a specific temperature, the distribution might look something like that. This is the average kinetic energy. That's what you measure when you measure temperature. If I increase temperature, here goes that. It shifts to the right. The average kinetic energy still increases. You've got fewer molecules going slower and more molecules going faster, but you still have molecules colliding with each other. You still have directions and speeds changing. As I continue to increase temperature, the thing continues to go that way. But there will never come a point where this curve looks like that. Okay? Or where all of the particles are going at the same kinetic energy. You can't have it. Okay? You can't have it. So the fact that the maximum kinetic energy they can achieve is reached at 100 degrees doesn't mean when the temperature of the water reaches 100, they are all going the same speed, okay? On average, they are going as fast as they can, but they're not all going the same speed. If they were, they would all exceed the attractive forces between them instantly, and you wouldn't have a bunch of little bubbles in a liquid, and the liquid particles are banging into each other. They're still changing velocity, they're still changing direction. You would have the entire pot of water disappearing instantly. So I do not agree with this. Now he gets a little more specific here, and this part I like, actually. Boiling point, vapor pressure, and volatility are three closely related properties that are all relevant to boiling. And you probably, or at least hopefully, you appreciate now why they are. Volatility affects vapor pressure. Vapor pressure affects boiling point. The more volatile a substance is, the higher the pressure of its vapor at a particular temperature. The higher the vapor pressure at a given temperature, the lower the boiling point is going to be. This influences that, which influences this. Okay? And again, vapor pressure is an intensive property. it can be used to identify a substance, and based on the amount of substance and the specific temperature, it's definitely intensive. We can quantify some of this now. And these definitions, we're gonna sort of overlay them onto the graph at the bottom of the page, which I asked you guys to look at. The heat of fusion doesn't mean fusion as a fusion reaction in a reactor, it just means melting. So heat of fusion means the amount of heat required to melt a specific amount of a substance at its melting point. Obviously, if you have more of it, it's going to take more heat to melt it. But the fact that it's specific to a particular amount means that it's an intensive property. So it's usually joules per gram, or as we're going to see later, joules per mole. It represents the difference of potential energy between the solid and liquid states, since only the substance's state, not its temperature, is changing. Now that's an interesting point, which we're going to explain when we get to the graph at the bottom of the page. Remember when we were looking at those arrows going in the up direction and the down direction? This diagram here. We said that although the directions were fine, the scale was wrong. So this is what heat of fusion would be for a specific amount of the substance, okay? When you go from solid to liquid. And the difference in potential energy is what we're referring to. But to go from liquid to vapor, it's much higher. You're overcoming far more attractive forces to go from a liquid to physically separating the molecules than when you go from a solid to a liquid. But we can quantify that. For a specific amount, say, of water, we could calculate the number of joules per gram that would be required to melt it. Have a certain mass of water, the number of joules per gram, or we're going to see per mole, to vaporize it. It represents the difference of potential energy between the liquid and the gaseous state, since only the substance's state, not its temperature, is changing. Again, that's going to play out on the curve at the bottom of the page. Up here he says the heat of fusion is released when the specific quantity of the substance that has melted now freezes. When it freezes, it's giving the energy back, it's releasing the energy. Because potential energy is decreasing, kinetic energy is increasing, which is where it's usually released in the form of heat. Same thing is true here. The heat of vaporization, the energy that it took to change a specific amount of the liquid to its gas, is released if you take that gas and you condense it, when the specific quantity of the substance condenses. Those are the down arrows. The heat of vaporization, as opposed to the heat of fusion, vaporization indicates the strength of the force holding the liquid particles together in the liquid state. And why that is because you are completely overcoming that attractive force separating the molecules. And again, it's measured in joules per gram, but after chapter 3, you'll see it's joules per mole. Now let's have a look at this graph. And I'm going to enlarge this a bit because I'm going to add things to it, okay? Which I would suggest you may want to do as well, because what I'm going to do here would make a pretty good test question. Okay. So we're going to start by drawing some vertical lines on this graph. Dash lines. section, we're gonna say something about the energy change. Now let's say for argument's sake that we started with a thermometer frozen in a block of ice. Doesn't matter how big the block is, but it's trapped in that ice. So we're gonna start down here at a temperature below 0, okay? As let's say we take the ice cube out of the freezer with the thermometer in it. The thermometer, let's say it reads, I don't know, -10 degrees Celsius. Ice can get colder than 0 degrees. But then we take it out of the fridge and put it on the counter, and you see the temperature of the ice going up. If the temperature is going up, remember what temperature is, it's a measure of average kinetic energy. So that increase in temperature must mean that kinetic energy is going up as I add heat, okay? If kinetic energy is going up in a solid crystal, I mean, what is that telling us? It's telling us that the solid particles are vibrating faster and faster and faster. They can't move from point A to point B yet, but they're vibrating faster. And that's what the increase in temperature is telling us. At the point where melting just begins, now what's happening? Those things are moving fast enough that they're overcoming the attractive forces within them, okay? And an increase in energy then is not kinetic. Now it's potential. We keep putting heat in, but as long as there are particles trapped in the solid phase that have having those attractive forces overcome, all of the energy is going into making that happen, not to increasing the speed of the particles. So from here to here, from the point where we first start to see the liquid to the point where there's no more solid, the only thing increasing here is potential energy. So this is what we refer to as heat of fusion. The increase in potential energy, the difference in potential energy from the liquid state compared to its original solid state. And in terms of states, here we have both solid and liquid, okay? So initially when the melting starts, we got all solid and no liquid, and then the solid goes down, the liquid comes up, okay? But that doesn't involve a temperature change. Where is that heat we're putting into it going? Only overcoming attractive forces, which is why it's a potential energy increase, right? Now, we've got landmarks here in terms of the temperature scale. We got 0 here, Celsius here, and 100 Celsius here. Probably means that what we're heating here is water. But anytime you see a constant temperature over a phase change, it means whatever we're heating is pure. It means there's only one thing there. So regardless of what these things are, even if I don't have 0 and 100, I would know that whatever I'm heating has to be pure if its temperature doesn't change during the phase changes, okay? And that's one of the ways we used to assess purity. One of the, I don't know, I think it was Chem 451 or something in university. We had to isolate different compounds, synthesize them. One of the things we did was extract caffeine from tea. So at the end of the lab, you had a little vial with these white crystals in it. And before you submitted your lab report, and by the way, organic labs were like 4 hours long. So at the end of that 4 hours, you had this little vial with these white crystals in it. And you didn't just write a lab report and give it in. You had to test your sample for purity. That was one of the things you got marked on. And how you did that, there were 3 analyses we did. One of them was a melting point analysis. And there's an apparatus called a melting point apparatus, and it kind of looks like this. This is just a schematic, okay? So you've got a temperature dial here. And you've got 2 or 3 holes up here, then you've got a magnifying window here. And what you do is you take little, tiny little test tubes, okay? They're like as thick as maybe thinner than a shoelace. And you scoop up some of the solid that you just synthesized, and you put it in the middle channel here. And then that little test tube, you see a magnified image of it in this window. So there's the test tube, bottom of the test tube in the window, and you've seen the crystal there. So then you turn the temperature up, and the thermometer's right here. And you read the temperature in the thermometer as you look at the magnified version of that solid. And as soon as you start to see a liquid form, you record the temperature. So we're melting it. And then you watch this and the thermometer. So you record the temperature at which you first start seeing a liquid, and then the temperature when all of the solid disappears. And if the substance is pure, there should be a very small change in temperature. Now let's say you sucked on the lab and there was a whole bunch of other stuff in there. Now the temperature is going to go up while it's melting, and that means it's impure. So as long as you don't see a temperature change on a phase change, it says that what's absorbing that energy is pure something, okay? We'll talk about what an impure sample might look like on this graph in a minute or two, okay? So you're heating it. Potential energy is the only thing going up here, which means all that's happening here is that heat is overcoming attractive force. As soon as the crystal's entirely melted, only now does the average kinetic energy of the particles start to increase. So as we're going here, this is now kinetic increase. Just like it was here, because the temperature was going up. We're still adding heat through the whole process. It's just that now it's increasing kinetic energy. And the liquid continues to heat. At the point, as we saw in our graph, when the vapor pressure of the vapor of that liquid equals atmospheric pressure, boiling begins. Okay? Now, all of the energy going into that is overcoming the attractive force between the molecules in the liquid phase. And compare the size of the heat of vaporization to the heat of fusion. This is way more. Okay? Obviously here what you have is a liquid and a gas. Okay? Again, its temperature remains constant because the only thing increasing here is potential. And Gary tells us the heat of vaporization is the difference in potential energy of a gas compared to the potential energy in the liquid phase. That's the potential energy we had to add to get all of that liquid to boil. Once the liquid is boiled away, and assuming you collect the gas, then the kinetic energy will go up again as you heat. The water vapor can get much hotter than 100 degrees, but water can't as long as it's at atmospheric pressure. Okay? Questions so far? Notice every one of these vertical sections had one energy change, either kinetic or potential, but never both. Where would both play out? Well, if what I was heating wasn't pure. Winter's coming, right? So let's say, I don't know, last week of school, you go outside and you look at the driveway, you're about to back your car out down and it's full of ice. What are you likely to do besides take a snowmobile? Let's say you have to get to school. One of the students in the other class said, get a shovel. Well, the shovel would get ice off your driveway, yeah? Put salt on it, precisely. If the salt melts the ice, then presumably it must do something to this graph, okay? So Gary doesn't do it for us, but let's overlay on this graph what a heating curve would be if what we were heating wasn't pure. Okay. So when I throw the solid salt onto the ice, the salt starts to dissolve. Even at 0 degrees Celsius, salt has a measure of solubility. You guys remember this term, or this symbol last year from times 10, that little AQ? What does that mean? What does that bracket tell us? Aqueous solution of this. In other words, that's dissolved in water, okay? Now, when you take white table salt and throw it in water, it looks like it disappears. It doesn't disappear. What it does is the sodium chloride crystals dissociate into sodium ions and chloride. That's what happens, okay? It's called the dissociation equation. This is what happens when you throw a solid table salt. If you want to put an S there, that's fine. It dissolves in the ice. How would that change? Well, let's use, let's see which felt pen I have. This is purple's good. Let's use purple. So, the sodium chloride starts to dissolve in the ice and we're heating. So let's say we heat it. First thing you're going to notice is it starts to melt at a lower temperature. And the greater the amount of impurity, the lower the melting point is. And what do I mean greater amount? Well, the higher the concentration of these things, the more the melting point's going to go down. Okay? And remember, melting point is starting with the solid and heating it. Freezing point is starting with a liquid and cooling it. Freezing point, melting point happen at the same temperature, or temperatures. It's just the direction from which I approach it. So melting would begin here. That's the first thing we notice. We start to see it melting before 0 degrees, below 0 degrees. The next thing we notice is the temperatures going up while it's melting. Okay. And if the temperature's going up while it's melting, it's gotta mean, if it's melting, fine, there's an increase of potential injury, there must be. But if the temperature's going up, there also must be an increase in kinetic energy, because something else is in there. You can't have a phase change happening and a temperature increase unless there's at least two things in there. In other words, something is increasing in kinetic energy, but something's also increasing in potential. That means there's a mixture. That means it's impure. So not only will the melting begin at a lower temperature, and not only will the melting occur over a range, but when the solid's all gone, you still won't be at 0. Okay? So in other words, the melting point has been depressed. Okay, so let's say it's -5 outside and the ice is frozen on your driveway. You sprinkle sodium chloride on your driveway, it starts to dissolve, the ice melts. Why? Because as the sodium chloride dissolves, the melting point that might have been, or the freezing point that would have been 0, maybe it's now -10. And if it's -5 outside, it's going to stay liquid. You will have lowered the melting point sufficiently. Okay? Then you keep heating. So now you're not just heating pure water, you're heating salt water. Now you're going to see exactly the opposite. It's not going to start changing phase at a temperature lower than 100. It's going to start boiling at a higher temperature. How many of you have ever cooked spaghetti at home? Any Italians in here? No Italians? Ever cook spaghetti even if you're not Italian?
Oh, yeah.
What do the directions on the box say? Add spaghetti to what? boiling what? Salted water. Now, people think, well, you're adding salt for flavor, cool. You're not just adding it for flavor. The more salt you throw in the water, the higher the temperature before the boiling starts. Okay? Moreover, as it's boiling, as we're boiling salt water, what's leaving? Is it salt or water? It's water. When does salt boil? Well, salt doesn't melt. Table salt doesn't melt till it's 801 degrees Celsius. So it certainly isn't boiling at 100. So as you're boiling the water away, the salt is still in there, right? But what's happening to the concentration of the salt if the water's going away? Concentration's going up. In other words, as you boil the water away, these things are staying there. The water's going away, but the salt stays in there. So the concentration of the ions is going up. And if the number of ions goes up, so does the boiling point. So as it's boiling, temperature goes up. So spaghetti cooks faster. Now, after all, and again, if the temperature's going up, it's not just potential energy going up, it's kinetic energy going up, which means there's got to be something else in there. Something is increasing in kinetic energy, but there's something else changing state, which is a potential energy. After the water's all boiled and all the gas, then this and this are pretty much the same, because now it's just water. What do you have at the bottom of the container when all the water's gone? Salt. You got solid table salt. They didn't go anywhere. All that happened is the water left. So look at what we've done. We've extended the range over which this thing was liquid. It was liquid at a lower temperature and remained liquid at a higher temperature. The chemists often speak of boiling point elevation and freezing point depression. In other words, we extend the temperature range over which that thing stays liquid. Some of your parents probably have electric cars, some of your parents have internal combustion engine cars. I'm not sure what the cooling system is in electric cars, but most cooling systems in combustion engines are liquid cooled, which means you have a radiator and you have antifreeze in it. If you just put water in your radiator, then the water's going to boil. You don't want that. Also, if you put water in your radiator, it's going to freeze below zero, which you also don't want. But if you add antifreeze, which is usually, mechanics suggest a 50 mixture of water and ethylene glycol. Ethylene glycol brings the freezing point way down and brings the boiling point way up, because the temperatures in your engine can get colder than zero and hotter than 100. You want that thing to stay liquid at well above the extremes of where water can stay liquid. All right? And ethylene glycol is a compound we're going to talk more about when we get into organic chemistry, if we ever get there in chapter 8. And it happens to stick to itself even better than water does. So it makes that increase in liquid temperature range pretty efficient. All right? Now, if instead of a heating curve, what if we talked about a cooling curve? So instead of heat being added, what if heat was being removed, like in a refrigerator or a freezer? Well, let's say we started with pure water at 80 degrees. And instead of added heat, removed heat. So maybe I just overdo this. So let's say we started at 80 or 90 degrees. If it's pure water and then cooling it, it's going to look like this black one, simply the mirror image, because it's the same liquid being cooled, and energy is always conserved. So the pure water is going to come down here, the temperature is going to get colder and colder, until I start to see the first sign of solid. It will remain solid, in this case freezing, until it's all frozen, and then the temperature drop again. So it's gonna be the mirror image of this, because I'm removing heat. In this direction, I'm adding heat. In this direction, I'm removing heat. But the temperature changes, the phase change happens at the same place. Here, kinetic energy is going down. Here, only potential energy is going down, because the temperature is not changing. If I heated the salt water instead, let's say instead of starting with pure water, I cooled salt water. Well, it's gonna start melting not here or here, or start freezing. And then its temperature will go down here before it cools again. Again, the mirror image of this. And that's what I meant by saying freezing point depression lowers the freezing point or melting point, same thing. Boiling point elevation, right? Now this is beyond what you guys need to worry about, but when the city sands and salts the road, the sand is mostly for traction. The sand really doesn't lower the melting point that much because you have to have something dissolving in the ice. But what they mix with the sand is some salt. But usually it's not sodium chloride, or not all sodium chloride. It's often at least a mixture of magnesium chloride. Magnesium chloride works better than sodium chloride. Because when magnesium chloride dissolves, instead of just getting 2 ions, you get 3. You get a magnesium cation and you get 2 chlorides. So the number of ions is all that dictates how much the melting and boiling point change. And if you're salting the streets, then it's the melting point that you care about. The fact that this puts more ions per formula unit in the ice means it's a more efficient way of bringing down the melting point. Okay? Now that's, I'm not gonna ask you that on the test, but yeah. So, granted, that's kind of messy, but a version of that might make a good test question. So you ask, well, how could that look on a test, Mr. Toad? Well, let's say I asked you to sketch a heating curve. And I described, let's say it's pure ice that you're heating. Or maybe it's a sample of ice contaminated with sodium chloride. And if I ask you to draw both on the same curve, I should be able to see the difference. Okay? Everything we've talked about up till now, heat of fusion, heat of vaporization, boiling, vapor pressure, all of that, none of those involve chemical changes. But fear not. Here's several. Some chemical properties of substances. And again, a chemical property to be observed or measured has to involve chemical changes. So here's 3 references to chemical changes. Reactivity refers to whether a substance reacts or to its reaction rate. Some, not substances in terms of that table, but just as far as elements is concerned. Some elements are more reactive than others. So you guys, we're going to talk a lot more about the periodic table in the next section, but this zigzag line here separates metals on the left from non-metals on the right. So most of the elements in the periodic table are metals. And we'll talk about what properties of metals involved. But in this collection of metals, some metals are just naturally more reactive than each other. And chemical reactivity is all about valence electrons. In valence electrons is chemistry. They're the only electrons that take part in chemical changes, the ones on the outside. So if you can describe the electrons on the outside of an element, you can get an idea to some extent of reactivity, among other things. So, the most reactive metals on the table are these, the alkali metals. And they only do one thing. Alkali metals only ever do one thing in chemical changes. They give away an electron. Why would that explain why they're the most reactive metals in the table? In other words, if the only thing they ever do is give away an electron, why would that mean that they're the most reactive metals? Well, number one, they only have to give one electron. But why? Why would they want to give one electron? What's in it for them, if you will? They become, on the outside anyway, like a noble gas. Chemists have a term for them. I'll define it later, but it's called isoelectronic, same number of electrons. So, these are the atomic numbers. This is the number of protons, but also the number of electrons in the neutral atom. Look at cesium. It's got 55 electrons. If it loses one, it has 54. So it's easy. In nature, these things never react with anything, ever. Under duress, we can force these, argon, through radon. We normally don't worry about this. It's just a synthetic element. Normally that one, not that one either, because it's radioactive. But in nature, they never react. But we can force these big ones to react. We can never get these to react. So there's something about the noble gases, electrons, that make them particularly happy. Rubidium gives one away. It's got 36, just like krypton. Potassium gives one away. It's got 18, just like argon. Sodium gives one away, 10, just like neon. It's not hard to take a negative charge away from a neutral atom. It's pretty easy. Moreover, reactivity changes as we go top to bottom. As we go down this family, atoms get bigger. If all they're doing is giving away one electrons, it kind of makes sense that the biggest atom is going to give away its outer electron the easiest, because that electron is so far from the nucleus. So this is the most reactive metal. We're not going to worry about francium. It's there, but it's radioactive. So cesium is the most reactive metal. Most reactive metals in the table, most reactive alkali metal. If you take a fingernail's worth of sodium and throw it in a glass of water, they're all very light, so they'll float. And one of the products is hydrogen gas in that exothermic reaction. And if the gas is released fast enough, it'll ignite. So you see little sparks of sodium. But as we go down, it gets more scary. You put a little fingernail's worth of cesium in a glass of water and blow it. And it won't just blow up the glass, it'll blow up whatever's in the vicinity. Same reaction, it's just happening way faster. Obviously, that's a chemical property, right? These are the most reactive metals, but the most reactive elements are the halogens. And the most reactive elements are never found in nature in their elemental form. We never find sodium in the ground. It's a compound. It's so reactive. We never find the halogens naturally as elements. They're always in compounds. That's how reactive they are. What do the halogens do in all of their chemical changes? Well, they're one electron short from the nearest noble gases. All they do is grab one. And it makes sense that a little atom is going to be able to grab an electron easier than a big one because the outer electron cloud is so close to that nucleus. So whereas the alkali metals get more reactive as they go down, the halogens get more reactive as we go up. These are not just the most reactive nonmetals, they're the most reactive elements. And if they get more reactive as we go up, that must mean that is the most reactive element in the table, and it is. So the most reactive elements in the table are top right, where it's easiest to gain an electron, bottom left, where it's easiest to give electrons. And that's just in the context of this. And we haven't even talked about compound reactivity, but obviously it's a chemical property. Okay? Heat of formation. Heat of formation is the heat released, which suggests it's an exothermic event when a substance is formed from its elements. So let's say I take hydrogen and I react it with oxygen. What type of reaction is that? Remember the types of reactions we talked about? Synthesis. So these are synthesis reactions. So when you make a compound from its elements, and if you get a university text and look at the appendix, there's pages of what we call thermodynamic data, just data. And every compound, as part of the thermodynamic data, has a little symbol like this at the top. Okay, that's called the standard heat of formation. And we're going to learn in subsequent chapters that for an exothermic reaction, delta H is always negative. So it's got all these energies. The amount of energy released when a particular amount of a substance is made from its elements. Okay? Because elements are elements, they obviously have zero heat of formation. Because if they're already elements, it's just zero. They're already there. We're not making them from anything else. Heat of combustion. That's the energy released when the specific amount of a substance burns in oxygen. And again, usually it's joules per mole. We haven't talked about moles yet. Gary says joules per gram, it's joules per mole. That's the SI unit for amount. But point is, all of these are chemical properties. You don't have to worry about the definition for these yet. The big takeaway is just they are chemical properties. So if you look at this table down here, let's divide it in half. Here we have four substances: methane, which is, you don't really need to look for, methane is CH4, ammonia is NH3, we know water, and magnesium is just an element, okay? So, methane melts at negative 182.5, which is pretty cool. It boils at minus 161, which is pretty cool. This must mean that it doesn't stick together very well. The molecules don't stick together well at all. And methane is the main thing that comes out of here when I turn on these gas jets, all right? Main component of natural gas. Heat of fusion, the amount of energy it takes to melt a gram of solid methane, 69 joules. A joule is a tiny amount of energy. As you guys know from specific heat last year, to increase the temperature of 1 gram of water 1 degree Celsius takes 4.2 joules. So that's not a lot of energy at all. The amount of energy it takes to boil it, the heat of vaporization, notice how much more it is than the heat of fusion, which is always the case. So there's the first takeaway. Ammonia. Ammonia is less volatile than methane. It's got a much higher boiling point. It's still cold, but it's much higher than this. It takes more energy to melt this if it's sticking together better. And again, to vaporize it, notice, again, much more. Water, it's got a very high boiling point for its mass. It's kind of unique in the chemical world. To melt it, 334, almost the same as ammonia, but to boil it, it takes way more, about almost twice this. Now, magnesium's a solid, so obviously its boiling point and melting point are a lot higher. Heat of fusion, though, isn't that much different. In other words, once we get it melting, the amount of energy it takes to melt per gram is not that dissimilar from water or ammonia. But the heat of vaporization is much more. Now, if you shift the column to the right, now we have two chemical properties. The big takeaway here is compare these numbers to these numbers. Heat of combustion compared to either of these is massive. Every gram of methane releases 54,000 joules of energy when it's burned. Every gram of ammonia releases 22,471. Again, these numbers pale in comparison to the chemical energy changes. And remember, that was one of the criteria for how do you know if a chemical change is occurring. A significant change in energy. Physical changes involve energy too, but they're just tiny compared to chemical changes when bonds are broken they form. Heat of formation, again, much bigger than any of these. Now, why does water not have a heat of combustion? That's kind of an easy one. Because it won't burn. It doesn't burn. If it's not flammable, it doesn't have a heat of combustion. We use water to put fires out, but it doesn't burn, okay? Heat of formation, quite a bit of energy released when water forms. It's interesting, I can leave hydrogen and oxygen in a container for 100 years. Those molecules banging around hitting each other. And after 100 years, there's no water in there, which is kind of a weird one. Why not? We'll explain why that is when we get to, and those of you that I taught Science 10-2, I already know, but we'll explain that later. Why does magnesium not have a heat of formation?
Because it's an element.
It's an element. The definition of heat of formation is to make a substance from its elements. If it's already an element, zero heat of formation. All elements have zero heat of formation. Now, I don't usually spend much time on Gary's review questions. Some of them are better than others. Let's see. What's 7? State whether each phrase refers to a physical or a chemical property. I'm assuming if we just say that, then yeah, physical. Relationships or interactions between matter and energy, that's both. That's both. Physical and chemical changes both involve these. Now, I don't know what he's referring to, what the answer to would say, but this has to be chemical and physical, even more chemical than physical. Only evident through a chemical reaction or lack thereof. Well, obviously that's chemical. Dependent solely on the relationships between the material's own particles. Well, that suggests there's no new bonds forming, so I would say physical. Relationships and interaction between different forms of them. Yeah, I don't really like that either, though, because if I take solid table salt, that's clearly a different form than liquid water. But if I dump it in and it dissolves, that's not a chemical change. So I think what he wants here is chemical change, but again, it's just not worded that well, which is kind of a hallmark of Gary's work. What else do we have here? State whether each of the following physical properties is physical or chemical. Vaporization, physical. Heat of formation, chemical. Corrosion resistance, chemical. Corrosion is, well, it's the reaction of metals with basically oxygen. And if it's iron, we don't use the word corrosion, we use the term rusting. But it's definitely a chemical change. Electrical property. Yep, electrical resistance, a physical property. Flammability, in case you didn't know what that meant. How easily something will burn or ignite. Clearly chemical. Speed of sound is physical. The defining physical properties. Well, we've done that. Let's see some of these. Students change classes at designated times throughout the day. With Sherry stuff, as you move on, the questions usually get better. Okay? With Gary's stuff, it's just clear he ran out of ideas. Students change classes at designated times throughout the day in most secondary schools. How is this event like a chemical change? It's not. You're still the same people. You don't turn into anyone different in here, do you? I'm not, what the hell? Let's see. I think there's even a better one here. Sensorial properties describe our senses of a material. Rather than being the properties of something, they are actually the operations of our interaction with that thing. Are sensory properties such as taste or odor properties physical, or are they chemical properties? Okay. We'll just skip that one. Okay, so there's some good questions there, but generally, no. So I'm probably not going to get too far in this, but from the matter map you just picked up in the introductory page, classifying matter seems to be the topic here. Now, my matter map is a little bit different than yours. Number one, I different stuff down different sides. So he puts the mixtures down the right-hand side and the pure substances down the left-hand side. I do the other way around. I also like this one because it's the whole matter map on the same page. He kind of builds it piecemeal, right? But I want the whole thing on the same page. Also, there are definitions of each of the terms here. What a pure substance is, what a mixture, homogeneous, heterogeneous, ionic, covalent, metallic. Notice there's holes punched in it. So put it in your notebook or your 3-ring binder, whatever. This is where we're going to start next time, okay? I don't think this will take us a long time, but there are a few things that we have to discuss when we're going through this. And you'll notice that there are some formulas here. He doesn't ask you necessarily to name the materials, just as ionic or covalent. We'll probably at least introduce or reintroduce some naming when we get to those practice problems. We're also going to say a little bit about, well, a lot about the periodic table, but I want to make a correction right off the bat. Astatine is not a semi-metal, okay? Astatine is a halogen. Full stop. It's not a semi-metal. It's not a semiconductor. These are 1, 2, 3, 4, 5, 6, 7, but not astatine. Okay. And this means they've just got properties. They're often called metalloids, semiconductors, semi-metals. It just means that under some conditions they can act like metals, and others they can act like non-metals. We'll be sort of jumping forward into, I believe, chapter 6 to get a little more, when we talk about the periodic table, a little more content on, you know, what it means to be a metal, what it means to be non-metal, that type of thing. All right? But I think maybe for today, because I don't want to get ahead of the class, we'll stop there. Maybe for next time, if you could, I don't know if I would worry about writing anything. How about you read from page 70?
Good afternoon, staff and students. As a faith and learning community, let us prepare ourselves for the end of day prayer. In the name of the Father, the Son, and the Holy Spirit. Dear God, today let us reflect on our relationship with you. We know that you are the way to peace and happiness, yet it is often difficult to take time to discover the way to you. Help each of us make this a priority in our lives and